Hi, this is Lab 3 of Macroscopic view of DC and RC currents. My name is Dan Killian. A little introduction. The purpose of this lab is to use fundamental principles to predict the behavior of circuits containing resistors in series and parallel, and then use multimeters to measure the actual values of conventional current and potential differences in the circuits and examine the behavior of ohmic resistors and capacitors. Summary of my results was the experimental RC value of 6.0. The fundamental principles used in this lab are Ohm's law, conservation of charge, also called the node rule, where the sum of the currents entering a node is equal to the sum of the currents leaving a node, and the conservation of energy, also called the loop rule, the sum of the electric potential differences around the loop is equal to 0. In this part of the experiment, we experimented with two resistors, 47 and 100 ohms, two ammeters, two batteries totaling 3 volts, and the surroundings are just the universe around the circuit. The calculated current was 0.02 amps because total resistance is just the sum of the resistors, and then the current is equal to the volts divided by the total resistance, which is where I got my value. When placing the batteries backwards, the ammeters read the same value, and when you replace the ammeter with the voltmeter, you have an open circuit, so the current is 0. In this slide, or in this part of the experiment, we were asked to measure the potential difference across different parts of the circuit. That's what I did here, and you can see in the table that these are my different measurements when using the multimeter, and I also graphed that same. I got the graph from the table, or drew up the graph from the data in the table, and you can see that it starts out at 3 volts, and as it goes through the different resistors, it drops back down to 0, which just kind of proves the loop rule can be used, because you add up all the potential differences and it ends up at 0. When I attach the voltmeter to the ammeter, it doesn't change because or when I attach the voltmeter, the ammeter doesn't change because no current flows through it. And when I replace the voltmeter with an ammeter in parallel with the 100 ohm resistors, the ammeter changed to 0.06 amps due to the node rule. At the bottom, I have the calculations for the different elements of the circuit, where I took the change in potential over the current. So for our 47 ohm resistor, we had 48. For 100 ohm resistor, we had 102. And then for the wire and the ammeter, we had both of those were 0. In this RC circuit, we used a 9-volt battery and two different light bulbs, 10 and 20 ohm light bulbs, and a 200 millifarad capacitor. Originally, when you get the circuit to go, the light starts bright and slowly dies while it's charging the capacitor. Then, after disconnecting the battery and connecting the capacitor straight to the wire, to the 10 ohm light bulb, the light does the same before, except that the capacitor is now discharging. In both scenarios with the 10 and 20 ohm light bulbs, the current decreases to 0 where the light bulb goes dark. For the 10 ohm charging, for the 10 ohm light bulb, charging the capacitor took 7.4 seconds, discharging took 8.5, and the 20 ohm took 6.3 to charge, discharge took 7.3. In this part of the experiment, we were looking at the time-dependent voltage across a discharging capacitor. We used a 30 ohm light bulb, 9-volt battery, and 200 millifarad capacitor. We charged up the capacitor with the battery, then removed the capacitor from the circuit, reconnected the circuit, and we started a timer when we did that, and just watched the voltage and watched it at certain times to see how quickly it was dropping. We were able to linearize our data by plotting our time versus the natural log of our voltage at that certain time over the initial voltage, and we found that the slope of that trend line on our graph was negative 0.1661, which, as we know, is equal to negative 1 over our RC value. So I calculated the RC value to be 6.0205, which is pretty darn close to the theoretical RC value of 6. Some what if questions. What if you were doing this lab in real life and use an actual ammeter? Well, In the experiment, we assume that our ammeter has zero resistance, even though in real life this is not true. Current in real life would be marginally lower. Then what if you were doing this without real life? We used a real battery to charge a real capacitor with no resistor in the circuit. How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? In real life, even the wires had some level of resistance, so it would have taken longer to charge. Thank you.